Hey everyone, this is it. I mean, our book is done. No, it's not done actually, is it?
Oh, I'm sorry. I made one chunk of progress, and believe it or not, that transistor is driving me nuts.
Yeah, there's one transistor in the universe that's not working right. Until we get it right, nothing is good. But yeah, this is the 10th day, I believe. Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Yep. This is our 10th day. We started on July 3rd, and we are now on July 12th. Happy birthday, Michael DeHilster. I know he never watches these, or he's not watching live now. So if you are, that's
I
he
think he's
accidentally.
cooking dinner right now.
Yeah, well, he doesn't watch us. I don't think he. I think he's really scared that we are like making giant fools of ourselves with our book. So people who are close to you and they don't say anything or do anything or pay much attention, they're going, is this about their book again? But of course, then when it becomes world famous and all that, then we'll disavow all of them and say, "Where were you?" But then when their worst nightmare comes true, then of course they'll be vindicated. But anyways,
I'm prepared either way, I think.
yeah. Well, we have enough people that we trust that they know what we're doing, and you know, it is like Amnon said. It's not whether it's right or wrong. It's the first out there really to have this breadth, and I do agree with that. And I've been around these kinds of ideas for quite a while. But anyways, what did I do today? Well, again, this is our last day in this series because tomorrow I go back to work during my day. I'm not retired yet, like my father, who has a well-deserved retirement because when he retired, he went directly into his wood shop, which he had prepared, had a
I
lot
did
of
buy some
wood,
stuff.
and then yeah, he did, and he bought all this stuff, and he's been woodworking for how many years now? None, because he's been doing physics. So the world, as I say, has lost a lot of
Carpenter.
poorly made furniture and wooden objects, and maybe has a masterpiece of a physics. Uh, but
It's an expensive way to create wood fire.
yeah, but anyways, we have come to the end. Today I worked on writing. Believe it or not, it's the title is Principia Mathematica 2, Universe Hack 3.0 toolkit, a complete toolkit for the universe, for hacking the universe. And I did not have hacking defined. Universe
Yeah, I wish
hack.
you would have told me that way back when we
Yeah.
started. When you told me we were hacking something, and I was pretty upset.
Yeah, because he thought hacking was a bad thing. But regardless, I did write that in today. It's pretty good, actually. So that's part two. Part one of the foundation. Part two is a hacking, where we talk about Newton Lesage. Dad wrote about that. I wrote Borchard and Deneau. And then we have our own hacks. And that's what Dad's been mostly working on. And then the other thing I did today was write some more JavaScript code to do some. I'm going to show you one white light because my dad showed me his picture of white light, and it didn't look anything like this. Well, sort of did, but people are going, "What is this?" Well, just for people to understand, of course, our um, white light. I mean, our light model is my father's light model, which is waves of particles. You can see them here, which are, you see these waves. You can see that this is blue, there's green, there's red. And the idea here is this is white light, and these are a small wave of blue light. This is a small wave of green light, and then a small wave of red light, which you can see that are further apart. And then this comprises white light. So he had in his diagram just solid sort of blocks or somethings for these lines.
Just arrows without the arrow point.
But regardless, I
So
put these together, and I had to write a little program to do it because it's a lot. And you can see that they're sort of randomly placed, but they do have. Again, I wrote some JavaScript for that, so I did that. And where I can say we are, where I'm at, and what I think we've done during these 10 days is basically I've come up with a vocabulary. I did a lot of the new graphics I wanted to do. Believe it or not, I didn't do any graphics for the circuitry, but I do know and had a couple meetings with my father during the week about I know how I'm going to be doing the circuit graphics. So there's quite a few. I would be very I would be not far off thinking there's probably 30 to 40 graphics that need to be done. But the good thing is during this week I got very good at working with Adobe Illustrator is what we're using. So, and programming it to get sort of the way particles that we want. You saw the particles that we want to have in the book, and we want it to be pretty realistic. See if I don't know if I can I zoom in on this. Hold on. There we go. So I can really zoom in on it, and you can see here. Those are all basically. Let's see, put us there too. Those are all drawn, generated randomly. You can see some have two lines, and those lines are the direction going, and some of them have two or three. So they're like motion lines. That's what those things are. So that's being drawn with the program, and you can see the red light. And then I also wrote the program today to make them come in waves. Before I was having to do that by hand. I said, no, this is ridiculous when I have to do something at this magnitude. And then whenever I have to draw a new diagram, I don't want to keep just copying the same ones, because the idea for me is the graphic person doing the book is that I want it to reflect the model, which is, no two things are the same. In fact, even the size of these vary slightly. Well, maybe these don't, but most of the time I do. Anyways, I'm pretty happy with the vocabulary I've really developed. I think that once I do one or two of the circuits, it'll go pretty fast. And this white light that you saw there is going to be incorporated into another big one, which is really important, which is dispersion, and which is basically how white light turns into a rainbow. Why would a triangular piece of crystal or whatever it's called,
Glass or crystal,
turn white light into a rainbow? But overall, I'm pretty happy. I knew we weren't going to finish the book, but the other thing I think that's really important is we went over on Saturday. We went through the book.
I remind you to bring that up.
Yeah. Well, first I wanted to tell you what I was doing today. Well, why don't we do that? What did you do today? And then we'll talk about our sort of wrap up.
Well, part of the transistor explanation involves how the G1 particles split inside the transistor. The emitter G1 particles come into the emitter, and some of them go to the base, some go to the collector. And the question is how they do that. Well, actually, Dave and I got into a discussion on Saturday about my explanation of how that's controlled, and it is based on the concept of parallel resistors, which is also in the book. But I realized then that my explanation for the transistor and how it splits would be improved if I went back to the parallel resistors and redid it. Well, I didn't redo that so much as I referenced something in the appendix for those who are interested, quote, in the equation for how you calculate the value of a resistor in an engineering sense. There is it's an empirical equation. And I went through and explained that so I could explain that the resistor value is inversely proportional to its G2 mass. Just to make a quick statement and not get over involved, but the value of a 3K has twice the mass as the value of a 6K, which is opposite from what you might think initially. And this appendix goes into the details. So those who might be interested in that, I added that this morning to the as an appendix. And with that, when I go to the transistor and I say I'm going to say it splits due to the fact that this resistor has a G2 mass and this one has it, that it splits according to the inverse value of the resistor. There's a physical reason. The appendix explains the physical reason in the transistor. I'm not going to explain it all over again. Just reference the appendix and go on and say, yes, it splits this way and these are the values. So so that simplified my transistor problem. But the last thing I did happened this afternoon, and I've been trying, I explained, at least in some fashion, the IV curve for a diode, and now I want to do it for the transistor. Well, that became almost impossible until I finally realized that for any reasonable explanation of the IV curve, I'm not going to explain an IV curve because it's difficult for a specific reason. But I remembered there's a load curve that you overlay onto that, which shows how when the current changes, the base current changes, the collector current changes, and you get a load line that you plot over the IV curve, and you can now use that to explain the load line. And the only explanation I have for the IV curve itself is that it's a brute force measurement of put this much current into the base, you get this much current through the collector. More current in the base, more current in the collector. Less current in the base, less current in the collector. And there's a whole set of curves based on base values of what that is. But to try to explain that curve, it's got a horizontal line, and what do you pick on the horizontal line to explain? I was stumbling over that over and over until I remembered the load line. So instead of explaining the curve, I'm going to explain the load line, which really helps explain the transistor function better. But I'm going to explain it using G1 particles flowing through it and losses of G1s as they go through the emitter, base, and collector. So I am still working on it. This is probably my third time through that thing. It's been hard.
He's cried a few times.
Well, when I design circuits with transistors, what you do is you look up the specification. You know what you got to drive, so you know how much current you got to have output, so you pick a transistor, either PNP or NPN, and you find out which one has the ability to do the current. You know what voltages you have. You got to pick. You can virtually do cookie cutter type design with a few parameters, and you got your circuit. And yeah, you may have to tweak it. But I never had to go through and explain the IV curve. I mean, never.
The IV curve, which is IV is the stuff that grows on your wall.
Yes.
Yeah, I know. He's using a lot of terminology, but it's from electrical engineering. And part of the book, a good part of the book, is how the particle model explains the electrical engineering, because it can. And one of the things you want to show with a model is extensive, how do you say?
Application.
Well, it's even more than that, Dad. It's more like, the way I would put it, one of the reasons people are going to say, why do you have so much electrical engineering or circuits in it? It's because it gives you a very good example of two things: in-depth application. And the other thing is it makes you look at it very differently. And then once you do look at it that way, would you say, my question to you as an electrical engineer in the particle model, do you think now when you look at circuits, look at him, he's shaking his head no. Do you think when you really look and think about circuits, when the physical part of them, it's totally different than the way you used to think of them for 40 years? I mean, the physics of it.
Yeah, it's amazing. you can learn how to use the equations and the specifications, design circuits, make it work, and earn a nice living.
Without
But
knowing.
without being able, sometimes without being able to visualize what's happening. Right?
What do you mean sometimes? I want to ask you how many times you have ever visualized the physics of what's happening in a circuit.
Only to the extent of what they told me was going there, that holes are flowing.
But how many times? Okay, let's go back because we're still not going to. So I would say once a year in your evaluations. So 40 times in your career, when your boss came to you, he says, "Okay, let's go over the physics again, and that there are holes moving." So in a 40 span career, how many times? Almost none.
None. No.
So I mean, you go through all of electrical engineering without having any idea really of what's going on. The most maybe you could say is there's heat or something like that,
Yeah.
or maybe there's a magnetic field or there's something you have to isolate. But it's all recipes, it's all equations, it's all rules, and if you ask, what I'm sure there are tens of millions of electrical engineers on the planet Earth, if you ask those people what's really going on in the physical part of these things, they don't know. They have no idea.
Yeah.
And they don't even know the bad explanation from physics, right? Because it's so confusing.
Well, and the interesting point is, once I went through the resistor battery circuit, which was the first one I did, and I understood, or at least I understood how you apply the particle model to that. All of a sudden, I can actually sit here and visualize what's happening through the circuit. Once you throw the switch on, what's happening, how it's building up, how it gets to stay. I can see this in my head.
Now, see, that's what I'm saying. This is one of the things I want you to remember. We have it on film now, on video, live here. But that's one of the things you need to write in your implications part. Because what you need to do, I think, is be extremely important, especially because I think electrical engineers are going to really like this book. And I think they're going to like this model because the people I know in our group who are electrical engineers are the kinds of people who are interested because they're interested in the real stuff. Because I think what it is, even though electrical engineers aren't dealing with the physics of it, they do have this emotional idea, especially with we software people, that they deal with real things.
Yeah, it's a resistor.
But they don't have a picture. So you have the unique point of view where you are the only EE person who knows the particle model, and you're a very accomplished electrical engineer. What now? You talked about that. You need to write that down give that perspective. You say, I'm an electrical engineer, and I see things different, and you say exactly what you did.
And when I got to the copper wire and battery and generator, I figured out how the G1 particle actually does escape from the wire. I was never taught that, but now I can visualize these things spiraling through in some pattern, escaping out. I never thought they escaped. Now I have them escaping and going around in a spiral, making a magnetic field. You can see this happen.
Well, what's bizarre to me is that you're an electrical engineer, and when you really look at these things, even though there's heat being built up, I mean, think about it, Dad.
Yeah.
I'm not an electrical engineer, but I'm imagining this. You're an electrical engineer, and you've got the particle model now, and you've got particles going around it, what they call electrons. But we have the G1 particles going around and around, and you say, current is going around, and it's heat. This resistor heats up because it's resisting the current. But there's no explanation what that really means, right? There's no explanation. Like, think of the simplest concept. All these tens of millions of electrical engineers out there, especially even younger guys who are just learning, they all know and have a feel intuitively what that means in a circuit, but they don't think about the so simple thing as, if less current is going through it, where is it going? Really?
Yeah.
Because if you're what as you as an engineer, electrical engineer, let's take yourself 20 years back. If someone were to walk up to you, and if you can put your mind into that point, and they said, Bob, like maybe I did, hey Dad, there's a resistor and there's current, on this side and less on this side, right?
Not in a traditional model.
Okay, but what do you say, voltage?
Voltage,
Okay.
less voltage.
Okay. Sorry, folks. Scrap all that.
See,
put
he's not an
voltage.
electrical engineer,
Right,
but
right,
the
right,
point's
right.
valid.
But so what it is I know there's voltage, and this drops the voltage. Where's the other stuff going? What would you say? Heat?
Probably, yeah, probably. Heat. Yeah, in fact, heat is probably the right answer because the ones that hit the atom and bounce away
Right.
are the atoms that cause is the force that cause atoms to vibrate, and that's heat. I remember when I was doing a lot of watching and generating of videos for the Gravity Interest Group and others.
Mm-hmm.
I remember two guys talking at the same time back and forth to each other on a video conference, talking about the fact that heat was really vibration, and I'd never really heard about that.
Really?
What do you hear about in heat? Entropy and enthalpy. Now, would you explain entropy and enthalpy? And the explanation is as vague as the name. Entropy is chaos. Things go into chaos. That's a big difference. That's a hugely different statement than a G1 hitting an atom and causing it to vibrate, and vibration is what causes things to heat up. Lack of vibration, it makes it cool as it cools down. Solids that are vibrating stay close together. You get them too hot, they pass by each other, it's a liquid. You get it even hotter, all of a sudden they escape and it's a gas. I never heard that explanation. I didn't even know what heat was that was related to vibrations, and I didn't quite believe it when I heard it.
Well, see, one of the things is
but
people...
over that period of time and working on this model, that example of just sitting there as a solid, heating enough so that the water molecules now pass by each other instead of being locked, is water instead of ice. It's a beautiful explanation. So yeah, they're lost because of heat, because to cause that heat and that vibration, the G1 has to hit. And once it hit, it's not going to stay in circuit, it's going to go out. And so you lose G1s. At the same time, you're pushing the resistor, you're dropping the voltage, and you're heating it all at the same time. You realize the G1 pushes the resistor in the circuit.
Yeah. I know, it's weird.
I didn't know
well,
that.
but if you think about it, though, too, even Dad, it has to, because if it's heating up, it's vibrating. If it's vibrating, something's hitting it.
Yeah.
Right? So...
Yeah, in a resistor, we ignore the fact that the G1 push as it passes through, we ignore the fact that it's pushing because we got that resistor tied down to the circuit, ain't going anywhere. But you put a G1 through a ping pong ball, it doesn't heat it up necessarily, it pushes it. So it's the same interaction, different result.
Jerry says, that's interesting. I haven't heard that either.
Ether, you haven't heard that ether?
No. Either.
Oh, Jerry.
Hi, Jerry. Yes, thank you for dropping in. Let's see here. He actually has a question. But before we get to any of that, and I have to go get water probably. Excuse me. But, I'm sorry?
Just stop for a minute.
All right. Why don't you tell...
Want me to get water?
I'll get water for me. Talk about our 10 days and what we did. What you think we did in that 10 days. While I go get some water.
Summarize 10 days. Well, to talk a little bit more about yesterday in going through the book, we made a whole list of things that actually need to be done. And yesterday I told you I added that one piece, but Dave has done all these figures, and he loves programming in a program language to have it automatically generate randomness. There is a randomness to this, even though the G1 particle field, we look at parts of it that are organized, it's random. And Dave did a lot of work over the week to generate figures that such that every time he wants a stream of anything or whatever it is, that it isn't the same thing. My figures, I do it the same way all the time, but I'm not a graphics person. In my case, I went through the whole Hack 3 of starting with gravity, gravity 1, gravity 2. Just this morning, I defined how gravity, the fact that a resistor, this is interesting. A resistor, you put it on a scale, you can weigh the resistor and get the weight of that resistor in kilograms. That's G1 mass in our terminology. But in a transistor or parallel resistor, it's not the kilogram mass that's important, it's the G2 mass that the G2 particle acts on. And up to this point, the primary effect that causes G2 mass are I put it in the book today, is the G2 orbitals in the resistor. The number of G2 orbitals, you have lots of them, you got lots of G2 mass. You have few of them, you got small G2 mass. That's a preliminary thing. I think it's more complicated than that. But at this point in the development, that's the best I can do. And generally, at a superficial level, which is what we kind of been doing, we're not going real deep, but at a superficial level, the concept that the number of G1 orbitals in an object determines its G2 mass. The G1 mass is determined by a standard, the kilogram standard. The G2 mass has no standard, and so we mentioned that a couple of days ago, that David's trying to put his name on the G2 mass. Anyway, so the resistor has, because you have level 1 and level 2 in the model, you have level 1 mass and level 2 mass, and they're different because the G1 particle, speed c, is a larger particle, even though it passes through atoms and molecules. G2 is a smaller particle, moves much faster, can move through smaller objects, and the interaction is different.
Yeah, it is, because G2s will go right through everything. You can't measure stuff at the G1 level with G2s, because it's just like, it'd be like G1 particles go through the Earth. That's like gravity goes through mass. So, but going back to the major theme for tonight, before we get into any specifics of the model, is over the week. Saturday we went over the entire book. We went over all the pieces of it, and from what we can see, it's there. So that's good.
There could be more, but if we're going to want to get it out, you got to draw the line someplace.
It's 3.0, right, folks? Because they hack 3.0, then we can come up with 3.1 and 3.2 and etc. But yeah, so we went through it. We're pretty happy with the structure of the 3 parts: foundation, the hack, and then the future implications, that kind of thing. The biggest part, of course, is the second part, and the biggest part of that actually, well, it's not, if there's one theme, it's circuits, but it's not the biggest part.
It is the bigger part.
It's the bigger part, but it's not the biggest part.
And it's because I know the circuits better. I'm comfortable with what I'm saying.
Yeah, but the way I look at it, one of the things that I notice when, and I've got back here, you can see these bookshelves. I've got a lot of dissident books back here. I've got over 100 books from absolutely over 100 books from people working outside the mainstream, and a lot of great models. But what you don't see necessarily is the ability or application of a model that could actually change things. One of the things is everyone gives it lip service, is that a new model of the universe should give us new technological insights and give us more insights to do new things or to understand things that we know in new ways. And I don't see that happening with most of the books of models I see. The books for models, I'm not going to pull them out because I'm not here to say bad things about people or their models, because I think it's great. Everyone has the right and should do as any model they want to do and do it in the way they feel fit, and to do it the way they feel maybe the universe could work. But one thing I do not see is the taking the model and really in depth taking on a subject. And the electrical engineering and the circuits are absolutely an amazing, because one of the things is, oh, you've got a model, but what can you apply it to? Well, guess what? We're applying it to all of electrical engineering, which is a perfect example, because it is number one. Electrical engineering is probably the most important engineering that mankind has put together to date. Because if you look at the electronics that we have, they do more for our society today. I mean, the internet goes down, for instance, we're all dead in the water. All the electronics in our lives today, it's the most important, probably, technology we have. Yet, amazingly enough, it's one that we have almost no, I would actually maybe even say it's worse than zero. It's negative, because what we do have is so ridiculous and bizarre that current is the movement of holes, and electrons go one way, holes go the other, and they go at meters per second, when we know that electronics are flying out there at near the speed of light. So if you take this model, you can apply it to, let's say, the most important technology that's out there, that mankind's come up with, that we use every day, that anybody, almost every human who's in the modern world will tell you that's probably the most important technology we have. And then you say, hey, did you know that we have no idea what's really happening and why this stuff works? And then you say, oh, by the way, we have a model and we are applying it, and this is what we see as happening. That's to me is absolutely fantastic, I think. I mean, that's why I am super happy, because one of the things I predict the future, don't I, Dad? Didn't I tell you? I said, we need to apply this to electrical engineering. And I asked you, I said, this is going to be really interesting. Before you did this, I said,
yeah, you said it, you were afraid.
Yeah, I was like, whoa, because what I was afraid of is that with your own model, you would start balking and saying, nah. And it was actually the opposite that happened.
Actually, it was. Because I all of a sudden had an explanation for voltage drop that was so clear.
This is electrical engineer talking.
Even a software programmer can get it.
Even me, exactly. Even an artist, scientist, programmer guy. But
the hard thing, though,
hey, Farouk, how are you, Farouk? Good to see you.
The hard thing is, okay, so we've done that. We can explain parallel resistors. I can hopefully prove that current actually drops as you go around the circuit from the negative to the positive, not the current, but the electron flow, that it actually drops and it's not equal. So what? So right now, do we have anything that was
a battery? No, that's not it. No, that's not the answer.
No, I don't know. It seems to me it's going to take some time working with the model to actually find out something about it that helps the engineer, the scientist, to develop a better transistor.
I think there's already things there, Dad. I already think there already is there. And one of the things that is there technologically is the model you came up with for light. Because right now, they're using, you know, why would a diode or a LED, I'm sorry, why would a LED be much more efficient? Well, the reason it's much more efficient is because they're building circuits that when the G1 particles or electrons, whatever you want to call it, comes out, they say it's photons. When those things are coming out, it's in a much more efficient way.
Well,
If they have even a better model, they can even make LEDs better
well,
than they are.
well, instead of people like Edison and whoever developed the material for the red, blue, and green LEDs, having to do it by trial and error, once you apply the model to how it's generated and apply that model to the ones you have done, you may get a clue as to how to put the next one together to do. I don't know. Are you to have a flashlight that generates a gamma rays? I don't know. It's
Well, no, what I'm saying, I think people are. I mean, the whole thing is if you have a model, that's going to happen. Okay, let's get back to the theme, which is the end of a 10-day sprint. As my dad said, I did probably about one day, if you want to look at it, maybe more, maybe a day and a half of just programming to generate these. I've already showed you guys this, which are, you can see this is pretty neat. If you look at this, you can see the waves inside there. And I colored them just to make them, because obviously they're the same particle.
They almost look like ripples in water.
Yeah, they do. I mean, what I like about this is because they're randomly generated, there's not two the same, even though that the program to generate this blue streak is the same as this. The randomness I throw in there, and I put in a sine curve so that you can see that there's more in the middle and less here. Sort of, you are imagining that a molecular structure is releasing G1 particles, and they release them in these waves, right? And
Also,
and then
it kind of gives a three-dimensional image too.
right. So I spent time building probably out of the 10 days, a day and a half on the programming side of it. And then I did this today because I need to do white light, and this is white light. Again, I need to make one that looks identical to this, except there are no colors. The reason I put colors there is as I'm trying to show people that white light is made. In this case, we're showing three types of different colors here.
But it could be many.
But it could be way more than it is more than that in our opinion. But regardless, that was one thing. The other thing too was to do a lot of the diagrams. We already did a lot of the. Ooh, look at that! My face is in the way. That's why I don't go to that one. But I did a bunch of new drawings. So I'm redoing all the ones we had in our book before, and there was quite a lot of them in here. I've got a couple of ones sitting here. Oh, the Big Bang just fell down. But you can see here. There's one there. This was my dad's, explaining my dad's old stuff. So I have lots of diagrams in here. But I've redone these. You can see these are little particles, which I also drew. But these are even more sophisticated now than they were before. These were just like one with one little line behind it. Now it's more sophisticated than that. So I went through our book. We use overleaf.com, and I went through that book to our book, and I'm just redoing a lot of them. So I've done those. I'm pretty sure part one has got everything it needs. The only other one I may put in that part one diagram would be for no negatives in the universe. But I got a lot of good diagrams. I think I've showed you them. Weren't some of the ones I gave you, like the intuitions of throwing things and like that? Yeah. The big one to me is the one I have on the website, which are the 4 classifications of movement. That to me is, if there was any way that we would make a T-shirt of this model, that would be it. You would have those 4. We have that on our website if you go to our website. Again, we'll get to your comments. Don't go away. We will get to them. So if you go to the website, you can see it. It's called Movement Classification. Take a look at it. But I did that, and then I did some writing as well. Would I've liked to have done way more, and my goal was to do a lot more? Yeah. But I think on Saturday, our big meeting where we looked at everything, where, okay, I've done writing. I did, I would say, like I said, part one is buttoned up. Part two, which is hack, is doing really well. Everything before our hacks, hack one and hack two, are pretty good, and I think the graphics for that are done. Now I need to go through, and I already have started graphics for the R hack, and that's the biggest thing. So if you look at one thing I'm really going to be tearing through a lot is that, and then I also came up when talked with my dad about circuit, because he's got lots of circuits, and I came up with the idea of having the G1 particles. Resistor has more nucleons, and then just literally symbolically showing the movement of mass and where it goes. In the battery, I did that too. And so that a person who doesn't even understand electronics will understand it. They're going, oh, yeah, there's these particles traveling through. There's 5 of them here. And when you go through this resistor, only 2 comes out this side. And there's 4 that comes out on this side. Only 1 gets knocked out. Oh, they're getting knocked out. I mean, those kinds of things. So that's what I see. So besides writing, the only one that I haven't written, I think, is Deneau experiments, underwater experiments, because the Deneau effect, which is particles going in loops, basically we adopted that model for magnetism. That all magnetism is simply particles going in loops, and yes, that means that solar system in some sense is a magnetic object at the GA level, right? GA level. So if you go G1, G2, G3 going down, GA, GB, GC, and there's a GG. But regardless, I have to do that one chapter that isn't done, but I don't see that taking very long, and I don't know. I even did a diagram. You saw my diagram of the underwater experiment. I drew the whole thing. Looks pretty darn good. So that's where I'm at. So I see myself having some writing to do, yes, but mostly graphics. And once I get 1 or 2 of the circuits done, I'll be able to rip through all of them, because they're just a matter of copying, pasting, and making your little arrows into real movable masses is all we're doing, even like with the white light. So, and I was inspired, the last thing is I'm very inspired by my dad's, one of my dad's primitive drawings, and that's why you see this here. That's from his primitive drawing. If you stand way back, what you really start seeing are lines, colored lines. Blue is going to be much darker lines. Green will be less. It will be almost as if
light green, dark blue, and a really faint red.
Yeah. So, regardless, that was very inspirational. And hacking, what that will do is we'll be able to hack as well the dispersion of why rainbows happen. So, regardless, it was a really productive. I wish I had much more time. It's good to get away from it, because when you go so far at it, as the week was going on, my productivity was going down some. So because your mind gets totally saturated with this stuff. So, and Dad just kept working away. He's just been working on the book anyway. So it was mostly me, because he's working mostly full time on it because he's retired. And I'm still my job.
Basically, for that week, I started at the beginning of Hack 3 with gravity through light, magnetism, electrostatics, circuits. What I haven't done, there's 2 major sections that I haven't gone through this week. And that's chemistry and biology. Believe it or not, I got parts on biology. And
that's on the eyeball, right?
Well, it's the ear, the eyeball. It's about sensing heat in your body.
Look at my dad. My dad, it's people are going to look at this book and say, Dave, why'd you put your name on this?
No, but there are videos out there on particle.guru that I called the senses, and there's three or there's at least, I think, four of them. I explained each one. Start with the olfactory nerves, believe it or not, because of a video I saw, and then the ear and the eye, and then the sensing of heat on your arm, to show how I think in a mechanical world these actually happen. And there's really it's the light itself is even more important, using the particle model light. And what do you think? I'll ask the audience, what do you think happens in the retina of the eye?
You don't have to answer that. You know why? Because you're going to get the book. No.
I'm not answering it.
Yeah, I know.
But what happens when that light that Dave shows you hits your eye? What do you think's happening, and how does the signal get to the brain? That's what I was addressing, because I was applying the particle model to that event. It's fascinating.
Yeah. Okay, so I mean that's pretty good. So my dad started through part 2,
It's hack 3 and
hack
part
3.
2.
Yeah, hack 3 and part 2, and so that's what he did. So we're really happy. Like I said, the pieces of the book are all in place. Most of the text is in place. Most of the graphics are in place, but more than half of them have to be replaced. So that we have it consistent, and it's also gets away from my dad's shorthand, which of course he's very used to, but we're not expecting people to be used to it. So when they get the book, especially if they're not more technically inclined, that they're going to be able to see that. So very happy.
He doesn't like my stick figures.
So when you ask us the question, the obvious question is, well, Dave and Robert, when is your book going to be done? We're shooting for fall, and I don't see. I actually plan to do something every day, even if it's only 10 or 15 minutes. I will do something every day on the book. That's my goal. And then we were thinking about maybe once a week, or maybe once every 2 weeks, coming on and talking about this with our goals.
Summarize a week or 2 weeks worth of work just to keep you informed.
Right. So if you guys have any questions, I know there's a couple of people hanging around. I know Jerry and Farouk, maybe still around here, and I know other people do watch. So there is a question. I'm not sure. It was earlier. This is from Jerry Harvey. He says, which relativity concepts would you say you agree with? What seems the main problems? Is there anything that you've suspended judgment? Did you want to try any of those, Dad, first, since I'm always the one who goes first?
The question's about relativity in terms of you're not specifying special or general. I'm not qualified to comment on general. I haven't done that. I would point out one of the things that helped me with the video on where I said special relativity is not needed. The main point of that video and that paper had to do with the event of how laser light is seen in the first place, because you can't see it unless you got something for it to bounce off of. And secondly, once it bounces off of, it gets scattered in all directions. One of the directions is towards the observer that's on the spaceship moving by the Earth, and the other is seen by the observer on the Earth. But in fact, you could have observers all over the place, and they would all see the same event because the light is bouncing off of the same set of particles that's in the spacecraft. In other words, I suggest that, this is my wife suggesting, she says, Bob, if you're going to do that talk, I heard if you use hairspray, you can see the laser light going through the air to the ceiling. So I did that at that, and so when the light hits the hairspray particles, it bounces an image towards the observer on the spacecraft. It bounces an image to the observer on the Earth. And my question is, what would change that so that the image is different? Because it's one event, one scattering, same image, unless something changes the light from when it leaves this hairspray particles to the observer B, unless something changes it. I think they see the light, if the observer on the ship sees it straight up, one on the Earth is going to see it straight up. If you see it crooked on Earth, it'll be crooked, one way or the other, whichever way the light happens to be going, because it could move right or left due to the speed, but so you could see it this way or that way, but it doesn't matter. Whatever A sees, the guy B sees. The one difference would be if a ship's going away, it'll be redshifted. Whatever light you're using would be redshifted, or if it's coming towards you, it'd be blue shifted. Otherwise, I contend that that one event is seen the same by everybody. And that's not what special relativity says. It says because of the motion of the spacecraft, the guy on this ship sees it vertical and the guy on Earth sees it leaning forward. And I can't see that happening with the light explanation of the event of light hitting the hairspray particles and bouncing off. I just can't see that happening. That's why I felt it was why I wrote the paper. That's what proved to me that I thought they weren't treating light correctly. I even say at the end of the talk, if you have a model for light, go ahead and use it. Use your model, whatever that light model is, have it hit those hairspray particles. Tell me, or decide what happens, what A sees, what B sees. And see if you don't come up with the same answer. Or if you come up with a different answer, there's got to be something different about the light. But clearly I'm using the particle model.
Yeah, Jerry, basically the answer to most all questions like that, and I'm going to show you a page actually on our website for this book. We have what we call the ins and outs of our particle model. But most of the time, you can answer probably 98% of the questions. Does the particle model agree with standard model by saying there is no standard model? So, and what my dad was saying, oh, use your model. Okay, well, right now, complete models were really maybe the only candidate to do that physically for everything, because we're actually trying to do everything. Whereas most models are right now today are concentrating on the periodic table, or their ether models. So they
let's talk about his model for light specifically.
Right, but regardless of what it is, what you have to say to yourself is, okay, what's relativity based on? What's really happening in the physics and the world? The problem with relativity is they're talking about observers. They're talking about the observations, and they're talking about observations and moving events happening, and that the physics actually changes, which is, unfortunately, relativity has paradoxes with its own axioms. Look at special relativity. Special relativity says the speed of light is constant for all observers. If you take that into account, then that's why you have to adjust the physics of the observers so that they all observe C from the same light source. Otherwise, you won't have the constants of C. And then you have the second postulate that Einstein says, which is all physics in the same frame of reference, or the physics in each same reference frame has to be the same. Well, how can that be if physics is changing depending on what you see? And then what happens is when you have conflicting events that would say, oh, my mass should be increasing if I look at this. If I look at this, my mass should be decreasing. So the problem with all of that is special relativity, Einstein did not say what light was. didn't say what gravity was. Even when he says that gravity said was bending light, he said it was space-time, and he calls it the fabric of space-time. He calls it the space, space. It's a foam. They call it quantum foam. The fabric of the very fabric of time. You hear rubber sheets. You see, but no one ever tells you what the physicalities are. But let me show you the web page. And if you go to our website and you click on the particle model, that is here, I'll show you because you can see it. This is what it'll look like on your phone because I've made it smaller so it makes it look very big. Here you go. And if you click right just on the particle model, you're going to see this page. There's the scientist, its implication, and this is what is out in our model. It says right here, TPN has no need for the following modern concepts. All behavior observed in the universe can be explained by the particle model without these concepts or theory. Relativity, both special and general, right, because they never had and never talked about the physicality, really, of what those things they're talking about are, and so they got mixed up in all the mathematics and all the coordinate systems. Basically, relativity is a coordinate system problem. Dr. Karazani showed that the problem was relativity requires you put a coordinate system all over the universe. There's only one three-dimensional space, and the only thing we can do is move the origin, and there's only one origin at any time. The four forces of nature, well, the reason they have that is because there's no physicality for an electric field. There's no physicality for a gravitational field. There's no physicality for light. There's no, it's a photon, but it can't be a photon because photons are one particles and they can't transmit a frequency. How can one particle transmit a frequency unless you just put magical powers on it? You have all the decaying is also as a weak force. So you have all the forces. Don't need them. If you have a model of the universe, the only force in the universe is a moving mass in our model. The Big Bang's all predicated upon redshift, and we've talked about in our model, and even in philosophically looking at the Big Bang, there's a huge amount of problems with it. But in our model, light, there's nothing in the universe that goes in a straight line and goes for the same speed ever. I don't care what level in the universe you're at. I mean, if you think about it, right now, if you ask the average person who likes sciences, if I go in space and I throw this thing out, they always say the Pioneer spacecrafts are going to go out forever, and because there's mostly space out there and not stars, it'll probably go through the entire galaxy and never hit anything. Well, this sounds sort of like our gravity particle, doesn't it? It goes through the mass. But anyways, off track. But that goes through. Well, what's happening? Well, that's not the way the universe works. There's always stuff in the universe, and so empty space isn't empty because light's going through it, gravity's going through it. Forces in our model have to be something. So the Big Bang's out. Dark matter and energy, that's only because they don't apply Newton to. They apply Newton as a point mass. The galaxy is looked at as a point mass.
Excuse me, let me interrupt on dark matter. Jerry, I somehow got subscribed to Quora.com. You may be familiar with that. I get one or two every day. And one of the ones I just recently read, the guy's name is Victor Toth. And he was answering a question. I forget what the question was, but he ended up by saying the one problem he saw with relativity was dark matter and dark energy. He thinks, that's his opinion, that there's a problem there and that relativity has to change. Now, he's not saying what Dave and I are saying in this list at all. It's a totally different story. But here is a guy
scientist
who consistently defends relativity and points out this problem. And I think there are other problems. Dr. Unziker points out the problems about selecting all the constants that are needed to properly define all these particle models.
19
particles.
19 constants.
Yeah,
19 variable constants.
And one of the big questions. In fact, there's a series I did on that on quantum mechanics where there's 5 main questions. And right now, don't ask me to go over it, but I got videos on it. I did what I could about it, just to talk to my viewers, but there are some people who are sincere about relativity and they still have some concerns. And it surprised me when he said this about dark matter.
Yeah, it's surprising, but it's not, because you'll hear people once in a while. I think these kinds of things that are out there, and the things and the websites we have and all the videos. There is quite a lot of people out there. It's not a small number of people who question things, and especially today and age where we're questioning everything. I mean, we're told that there's weapons of mass destruction, and they're not, and we go to war because of it. So people's sort of, how do you say, they're skeptical about people in authority saying what truth is, and so I think people are much more open. But if you look again on this our website here, dark matter and dark energy, I have a really excellent, just look up dissident science and dark matter. I will show you how Newton describes both. I use my father as an example, one of the talks he did, and Cameron Rigbasol, which is one of our really great critical thinking scientists in our group. He did an excellent breakdown of galaxies into pieces. And again, this is all in my video, Dissident Science, Dark Matter, look it up. And you'll see all the graphics very well explained, showing you that, in fact, Newton explains everything you need. There's no need for dark matter energy. And I even show watch it. It's easier than me explaining it. The expanding universe, that's something also. It's sort of weird because the universe is everything. So how could it be expanding? The word universe in almost every language on the planet. Human beings have come up with a word to mean everything that exists, not pieces of it, not half of it, not one over here and one over there, not parallels, not multiples, but the universe. So the idea of spanning universe is a stupid, illogical even phrase, because the universe, what's it expanding into? Not universe. So that doesn't make any sense. Charge is a big one where a lot of people, even in the dissident community, get on our case all the time. In fact, they just say charge is a fundamental thing. Oh, okay, so here's a fundamental thing. I put a plus on a proton and a minus on an electron, and they orbit. Hey, there you go. How many people on the street who like science are going to be satisfied to say, well, that's the way the universe works? They're going to go, some fairy comes along, or some, pixie comes along and paints these things on it, and the universe somehow knows what to do with it. No, we have to have a reason for it. So there's no charge. Neutrons are, again, neutral. Everything's neutral in what we have. There is no such thing as charge. So that's silly. I didn't put proton because neutrons and protons are pretty. Neutrons are almost thrown out by some people and even mainstream. So we just say there's a nucleus. We're not saying what it is or how it exactly is. Electric fields, again, fields are mathematical.
Electric field is that force between that plus that you draw on the particle and the minus on the other one. Electric field goes from plus to minus.
Yeah, it just does it that way.
And what is it?
In fact, if you in a circuit go, like, buy yourself a circuit, make yourself a circuit with a battery and a light bulb and a switch, and then if you go and you draw the plus and minus, and then you race those and then switch them, the current switches. I'm just kidding. I'm being really stupidly facetious. Anyways, parallel multi-universes, plate tectonics. Actually, also no negatives. I didn't put that in here, but there are no negatives in the universe. Think about it, no negatives. And then, of course, in what we do support is expansion tectonics, not just because the evidence is there, but we also have a way for things to gain mass, which is basically the sun's blowing nucleons toward us all the time. You put together, you put nucleon with a G1 and you get them orbiting. Guess what? You've got an atom, and what is the mass of things? It's really the nucleus. And so there you go. An infinite universe, both in space and time. We believe that. Well, that's Borchardt stuff. And faster than light speed particles. Why? Because we believe there are more levels in the universe. Doesn't mean that G1s are going to go 80 times the speed of light, but it does mean that there are particles out there that are, and our model would show that would be going much faster than the speed of light. This is an indirect implication. So that hopefully will answer some of your.
It answers a lot.
Well, because because his question was let's go back to his question. It says, which relativity concept would you agree with? He also says, is there anything there that you suspend judgment? What seems to be the main problem? Sort of, what do we agree with, what we don't? So I just...
No, you gave a complete answer.
Sorry about the complete answer. I'm kidding.
Well,
Yeah, you're right. He was asking. Okay. Here's one. We're just going backwards now. Do no negatives mean no electrons? Yeah, if you want to be pedantic about it, yes. What it means are G1 particles, they're not electrons. And the reason we don't call them electrons is because there's no charge there.
Right. You don't want to identify with the possibility of charge. As soon as we say we have an electron, everybody's going to assume it's negative. And so we call it G1. It kind of evolved to that, but
it's a good name. It's a good nomenclature.
And instead of the neutron and the proton, we call it the nucleon, which is a generic name for proton and neutron. And we are saying that has no charge. So the nucleus is a bunch of nucleons, and the orbitals are not electrons, they're G1 particles, and they're all controlled by G2 gravity.
Right.
Because the only thing that can control a G1 particle that's moving at speed c is something that's moving much faster than c.
Right. So exactly. That's exactly right. So yes. And there is no negative. In fact, when you look at the graphs like even a graph for you were doing
your light, was there a negative particle in your stream of light?
Yeah, exactly.
There is no negative particle in the stream of light, and yet it's made of G1s, which we say are equivalent in some sense to electrons. But you either have a bunch and then none, and then a bunch and then none, but you can't have negative particles. That's one of the reasons we say there are no negatives in space. In fact, the sine function alone, trigonometric sine function, cosine function, forces math to have plus and minus when they don't need it.
Yep.
And one application of that is AC current. In order to have a value for AC current or voltage, you got to square the sign so that you flip the negative part up to the positive and you average it. In our model, it's all positive in the first place. There's no flipping.
Right. I mean, basically, AC is basically G1's going one direction, then G1's going in another direction. There's no positive and negative. This is a good question that you asked, and I do have an answer for it. Wait, did you say that some scientists don't believe neutrons exist? Yes. They believe protons and electrons to exist. They don't believe. They're looking less and less at the neutrons. Now, if you go to the average person who's not looking at this and really deep into this, they're going to say, of course, there are neutron stars, et cetera, et cetera, et cetera. But one of the people in our group, his name is Dr. Bill Lucas, who is a real brilliant mind in physics, very brilliant. He studies particle physics quite a lot. He's more of a traditionalist than we are, for sure. He has a very different model from us. He does believe in charge, and he does believe in electric fields and all those kinds of things. But what he does say, and he's reported, is that the people he knows and colleagues he knows in particle physics, the people who are more on the cutting edge on the theoretical side, in fact, are saying that there's a good chance there are no neutrons, that there would be only positrons. But again, we would just call them nucleons. And it's good because we don't get in that problem at all because we don't have charge. So there would, in our model, a neutron and a positron would make no sense because the only difference between those are supposedly the charge. I don't know if quarks make those things up and give them different, but quarks have charge, a third of a charge. Okay, that's really fun. So that's the answer.
There's a very last appendix in our book right now is comparing Newton's equation for gravity and Coulomb's equation for charge. And we're explaining there that when you get rid of charge from Coulomb's equation, you get exactly the same thing as Newton, except in Newton's equation it's G1 mass, and in Coulomb's equation it's G2 mass.
Yeah.
An interesting thing, because most people, when they see Coulomb's equation, they say, wow, that looks like gravity. And we're saying, wow, you're right.
Well, if we go to the Science Woke website and go to new theories, we go to particle theories. We're in there. We go to the particle model. Click on that. You guys are watching this. Let me get this banner off. And you come down here. Guess what? That's exactly what I have here. Let's see if I can make this bigger. I can indeed. I talk about our particle model a little bit, and it's pretty interesting here, and that's what we're talking about right there. You can see that there's the force equation for gravity. I'm going to get back to that one other question I think I had up there, but I'm sort of diverting here. There's the famous Newtonian gravity, and if you look down here, here's the famous Coulomb's. And you see it's very much the same, except for the Q's. You have M instead of and if you then look at what we replace the Coulomb's equation with, we have just the exact same equation as this, exactly the same. The only difference is it's the level down. These are the gravity that's at this level is G1 particles. The gravity for Coulomb, what they call Coulomb's law, and this is why it looks very much the same. This is not an accident. The only thing is we have a real model for it. Down here you have an electric field, which they don't talk about what the heck that is, and we do. So that gives a good example of that.
And those are all empirical equations. Those are not equations that for example, I have a gravity equation equivalent to Newton's, which is totally different, doesn't include G, does include mass. It doesn't even include R squared, by the way. But,
right, but
these are empirical equations, and they work. There's nothing wrong with these equations.
Yeah.
But we have an equivalent version of Coulomb's law, which is a second level gravity equation.
Yeah. So this just gives you an idea here. I'm completely lost as to where we were coming from that one. But sorry about that. It's not anybody's fault but mine. I should make notes as I'm talking here. But I think, I don't know, negative structures. Do you mean that scientists don't believe neutrons exist? Yeah. You were asking, was that other thing we were looking at from this page about what's included, this one here. Whoops. This one here. Oh, no. Got to go back further. This page. Yeah, this is from our book's website. You just go to it and click on particle model, and you'll get those things. I need to add the negative. I have it in our book, but I don't. Like I said at the top here, this is no, this isn't the table of contents. Sorry about that. But anyways, let's see. Here we go. Here's another question. Let's get back to some more questions. Jerry Harvey, didn't you say you don't believe in time dilation? You agree with the possibility that idea that light travels from one point to another? Okay. This is just, Jerry, it's my opinion that you're not, perhaps our definitions of time dilation and yours may be different. And there are some people who get into this argument quite a lot. Time dilation, the idea is there's something called universal time, whatever that is. And if you ask my dad and I, it doesn't exist, right? Universal time. It's the only thing universal time is you can say that it's this time in Switzerland and everybody gets their clocks off of it. But the idea that there's the universe has time, and that in parts of that universe things have the times can be different, and that just there's so many levels why that doesn't make sense. So it's just because light travels from point A to point B, it has nothing to do with time dilation. I mean, time dilation is an idea that for some reason in a frame that you're in, according to, and this comes all from relativity, it's the only reason we're even talking about it with the word time dilation, is that if you're in a frame of reference and someone else is in a frame of reference, those frames can have time dilation go on. That's why they say the two astronauts, one that stayed home, the twin, a real experiment, and the other twin went up into the space station for 100 days. They came back and they calculated he's 4 nanoseconds younger than his other. I'm sure it's longer than that. But there's a difference between slowing things down and what people would consider time dilation. Time dilation is this idea that there's some universal time and that somehow slows down. Whether it's in a frame only over here, again, that's a concept that just has so many problems. What we would say, and this is a very old term I did not come up with, it's called clock retardation. And clock retardation means that when you take a GPS satellite and you put it up in space, it slows down. Well, why does it slow down? Because the gravitational field is only microgravity up there. And yes, even atomic atoms are affected by gravity. For certain, we know that. So if you have an atomic clock, it's affected by gravity. It's not like, I think what people think is an atomic clock when you put it up in space, oh, it's not affected by gravity. Like, if you put a pendulum clock, like my dad has in his bedroom room, that works on the principle that it's all adjusted to work in the gravitational field near sea level here, and it's going on somewhere. You take that up into space, it's going to work? No.
Not the same way, maybe not at all.
Not at all, probably. So this whole thing about time dilation, you got to get it out of your head. Time dilation is not. People have tried to hook time dilation to the traveling of light over time. No, no. They're trying to walk their selves out of these problems
redshift that I was explaining the other day is slowing down the speed of the particle. Has nothing to do with what time you're using. You have to measure in a sense, but it's literally slowing the particle speed down. I was not suggesting that the clock was changing.
Actually, man, I won't tell you, Jerry, but we actually have a way for you to get here if you wanted to join us, because we can actually split the screens. This is a stream. We can take anybody in the world and have a video conference live. So, right now we'll keep it for this way, but we could do that in the future. So you said, I actually tend towards the idea that there is an absolute time that exists throughout the universe, regardless. And I will tell you why you tend for that, okay? And I'm not saying you're wrong, but maybe I'm saying that. Yeah, I disagree with that. The whole idea of absolute time has to do with coordinate systems. The whole thing about coordinate systems is measuring. The whole thing about measuring is knowing we use light to measure things, and we get so caught up into this relativistic idea, and the idea that there are, like my father said. In fact, my father said in his talk the same thing as Peter Marquardt says in my video in my film, and he says, relativity is a theory about events and effects, and the problem is as we know, events happen and people observe them, so the event is the same. The problem is relativity in time, and absolute time is setting there to see if there's some way. Michelson-Morley, we didn't measure the ether. We have problems with clocks on GPS. Is it that we get so caught up into that? And the reality is there are things happening that happen in the universe. A star explodes. That explodes at a time. Everyone who observes it's going to observe the what is coming from that explosion. Whether you're far away, whether you're close, whatever. But this idea of absolute time comes from our fixation on mathematics. It comes from on our fixation with coordinate systems, and we just got to get away from that. I know a little bit about math because I got my bachelor's degree in mathematics. I love math. But I also know math is just simply a way for us to try to predict things. The way I look at math is a way for us to predict things, for us to predict how much stuff we need for our yard. It's to tell us how much what size something is. It's the math tells us all kinds of things. What size, how much will this beam hold in this building? All the mathematics with that involved, but the moment we start looking at mathematics and this idea of time, there in the universe, I'll give you Borchert's example. I like to use Borchert's example of time. My father and I have a little bit different, but doesn't matter. It's the same idea. Time has to do with movement. Time has to do with something's here and here, and we know that there's over time that happens over time. So Borchert, which I think is the simplest explanation of what time is, it's movement. So the idea of absolute movement, that's what you're saying. So your whole, I tend towards that idea. When you say I tend towards the idea of absolute time, you're tending toward the idea that mathematics is really important in the universe, and it's not. And that's my opinion, of course. I'm not here to tell you you're right or wrong. That's, but I see that, and I hate to say this, but I will say it. It's sort of a newbie kind of person who is just starting out really talking to other critical thinkers who've thought about this for a long time. This whole thing about absolute time and space and coordinate systems and all that stuff, I know people, and even myself, I've been almost 30 years thinking about these things. I was in my 30s and now I'm 60. So we've thought a lot about these things. And so it's not something, a lot of us have come to the same conclusions. But that's what I would say. Be careful, because what you're doing is, in my opinion, you're imposing a coordinate system and a time system onto the universe. And I believe that it works that way. It's more like, well, I've got this system, and I think that this system's going to predict the way things go. And when it doesn't, I'm going to be like Einstein. Well, Einstein says, well, when it doesn't do it what it's supposed to, well, guess what? Then time must slow down. And math must increase.
Change the facts.
Yeah, the facts don't fit the theory. Change the facts. So,
math should follow the physics.
Yeah, absolutely.
And that's what for example, in the circuits, the equations I use in the circuits come from the theory of the particles moving through a resistor, hitting the atoms, scattering away, and losing G1s. And that's the math I use. Got 100 coming in, you got 90 coming out, you lost 10, that's 1 volt maybe. So the math I use matches the physics. People can get into trouble by saying, hey, I got this great math idea, let's see if I can fit it into the physics. Seems to be the wrong way, I think.
Yeah, it is.
I prefer
In fact,
it much the other way.
Absolutely it is. And I think that's what makes our model so amazing. And again, it's not because we're amazing people and we think we have the answer, but what blows my mind about the model that we've put together is that you don't have math. When you're hacking the circuits and I'm hacking like dispersion or something like that, which I'm still trying to hack, I'm not thinking of any equations at all. I'm thinking about the general intuitions, and that's in our book. And I'm not showing that to anybody because you got to buy the book. But in the first part, I literally say these are the intuitions you need, and with these intuitions you can hack the universe. And I think when you talk about math, you can get yourself into big trouble.
I even showed one time where when I was playing with my equation, I wanted to simplify it so the calculations would be easier. The way I simplified it out was crossing out two identical terms that were, x here and minus x there. I got rid of it. What I got rid of was the source of the whole function. It's like I erased those particles from existence. That's what you can do with math. Once you change an equation, simplify it that way, it's not representing the physics anymore. It's just it gets the math answer fine, but it's not physics. If somebody else uses that and applies it to another equation, they don't, and they just do it on an equation basis without looking at the physics, they got the wrong equation. They're not going to get a good answer.
Yeah. It says, why believe in time dilation? No. I guess the question would be, why do people believe in that? Well, they believe in it because they say Einstein is God. His equations are a fact in the universe. In fact, I've even seen some science fiction films say that they've, who discovered relativity on your planet? Something like that. So, anyways, it's just why I believe in it is because people believe in Einstein and they don't want to say he's wrong. I mean, it's unfortunately that simple. And I see. Yes, I know you're not. I will comment on this, and I know you've been thinking about this for 25 years. One of the things about being around other people, a lot of other people, you have to remember, I started out just with myself and Dr. Carazani in the early 1990s. 1996, I went to the first conference of critical thinkers that are all talking the way you and I and my father are talking today. And because of that, you really learn, and I heard over and over again things that even though I thought of a lot of things myself for many years, I realized that just because I have been thinking a long time about certain things doesn't mean that in isolation, or I'm not saying that you were by yourself, but unless you've been in a group, you realize that you can miss stuff and things can take longer. I mean, for instance, my dad, one of our debates with our particle model is, if I didn't come along and throw in all these things that I had collected over the years, like Denew and Borkert and other things as well, would my dad have gotten to this model at all? And there's a good chance he wouldn't have. He could have, but maybe not. And the reason we get to where we are is because we have interactions with people with other ideas or who have thought about it way more than we have. And even if we have thought about it ourselves for a long period of time, it's not actually the case that I'm right about it. For instance, I could, for many, many years, look, and plate tectonics, I knew about plate tectonics, and I've learned about that. It wasn't until 2008, and I thought about plate tectonics and dinosaurs and all those kinds of things and how big they were, and even had curiosity in my own head, why, my gosh, these things are huge, would they live in... I've thought about that, but I didn't come up with Earth expansion. I didn't come up with the expanding Earth or expansion tectonics. So it's not that I'm saying to you that you haven't thought of it or you're not a person who's been around it, but sometimes we do have people who have thought about it even in better ways, or other groups of people. So a lot of the things I'm telling you, I'm not the only person, and many of them I didn't have the answer to them. So I am sure there's things that well, absolutely, there's things that you know that are more truthful in the universe that I don't know, and I learned from you as well. So I think that's what I was mentioning. Let's see. The idea of instantaneous light is unpopular. Okay, so that was probably...
It was very popular at Newton's time.
I think it says I've been a new. However, I did question if light is instantaneous. It had been the idea for about 2 decades, possibly the idea is so well established and unpopular. Yep. You're absolutely right on that one. So he's saying the idea of instantaneous light is unpopular. Yep. I actually look forward to ways of proving myself wrong. Well, that's good. We get scared about our book all the time, because
I walked up 2 days ago and said, David, I think I'm wrong on this one.
Yeah.
And I was going to redo the drawings and correct it, and then he had to correct me back.
It's funny that dispersion, the whole idea of the rainbow coming from white light, we hacked that at least 3 or 4 times, right? We thought we had the answer. And I don't think we have the answer still. But we know what the cause of it is. We know that it's most likely it's the G2, most likely, but there's another problem.
It has to be a high-speed mass moving. If force is mass in motion, you can't gravitationally control the bending of light with something that's moving less at the speed of light. It just won't work. So, I mean, it may not be a particle, maybe it's a wave, maybe it's ether, maybe whatever it might be. Because we worked so much in particle gravity, it was natural for us to evolve to a particle for the G2. But regardless of what it physically is, it has to move faster than light.
Well, the whole thing is that in our model, anything that orbits or has a curve is caused by a gravitational field, what we call a gravitic field, a gravitic motion. And so if you have things orbiting at the subatomic level, then there is a gravitic field, and it's not going to be the same as the G1s because they are also orbiting. G1s orbit. So if G1s orbit, there's another gravitic field below it, and that's our rules of our model, right or wrong. So I question myself every day, and that's good. This is interesting. You said, I don't think you're meaning exactly Wikipedia. There is a page in which I'm listed as a crank, and the last time they updated was in 1997, I think it was. So I have actually had people go and do that, but I will give you a better wiki about me, which is if you go to this address, you go to dehilster. I'll do that now. If you go to wiki.dehilster.com, you will get this. I will show it to you guys real quick. And this is my Wikipedia entry that I would call real entry about me and my work, and who I am. This is our scientific wiki. It's called, you can get to it by going to wiki.naturalphilosophy.org. The idea here is that we have a Wikipedia about people who we think are very good scientists, or people that are working in the field of which I could never have this written in Wikipedia. So I know I've had people, I make a lot of comments on Einstein's Facebook page because I get a lot of people to my channel and people to our cause because there's a lot of skeptics on that page as well. And once in a while, the people say, yeah, I looked you up, and they put the link to this thing where they have a picture of me from almost 20 years ago. Well, let's see, 97, 2017, over 20 years ago, 25 years ago, and they call me a crank. But if you look at this page, in my opinion, I don't, you can look it up. If you look up David D. Hilster, this actually pops up in Google as one of the links. But I always put this link out there, and they shut up right away because I have a pretty long and distinguished career, not necessarily only in physics area, but obviously in my own area. So when you look at this, it's really hard to say people that I'm actually a crank. If you look at it, I mean, my art career is somewhat formidable, and also my computer career. I'm one of two people who came up with a new computer language that we're now starting to use in our company that they're extremely interested in. So and I've got a lot of accomplishments in my life because I'm 60, and all of us do things. My dad's in there too. If you look him up in Hilster, and
it's one line. There's one line about me there.
Yeah, it's not one line, and here I have to fill out a lot more. I don't have a lot in here, but anyways. That's not. It's not really a problem in my opinion. It's. I think one of the reasons we put these things up there is because exactly these problems. Because people, if an average person takes a look at my wiki, my real wiki, and my father's real wiki, they're going to go, yeah, these guys aren't cranks. I mean, you can see a crank from what they do and what they say and all those kinds of things. So.
Yeah, but with this Wikipedia that we have here. People can't go in and change it.
Yeah, that's and the philosophy is here. I mean, it does have it. It says Wiki rules here, and one of the problems with Wikipedia is it's basically the big concept, the big picture of what Wikipedia is. It's the consensus knowledge, the consensus repository for human knowledge. It is not for places for new ideas. It's not for 6 models of the universe. Maybe one of them will be correct. Those are not there. This is supposedly what we know today, right or wrong. The standard model is accepted, you guys, so we're not going to put in the particle model in Wikipedia. They don't do that. And if you have our Wikipedia open, people are going to come in and do the exact same thing they do with Wikipedia. I mean, there's just so many examples. Expanding Earth, which is expansion tectonics. The number one person in history in expansion tectonics, his name is James Maxlow. I tried to add his name as one of the proponents for it, which I have a bunch of other people that are his contemporaries. I tried to add it, they removed it. Well, why did they remove it? Because the guy's the best. Why? So Wikipedias don't work, so that's why we're closed. And you see our Wikipedia, it says our rules, it says why are we closed? Oh, we don't have very much on it. We have 10,000 pages of information. I had a database that I put in here, and eventually this will give out. But we are closed to the public. Open wikis by nature are consensus-based, which are not conducive to the advancement of science. Open wikis lead to marginalizing criticisms of mainstream science. Open wikis lead to marginalizing and pseudifying science alternatives. Open wiki gatekeepers are arrogant, and most of them are intellectuals and not critical thinkers. So that's more or less. I think you're quite a progressive thinker, though. Oh, I'm a crackpot. No, I'm a crackpot. Okay. We've been an hour and a half. I mean, if we've exhausted Jerry's questions, oops, here we go. Let's see. What did you say? Here we go. How to know that you're correct about any of your beliefs? Right. If you're way outside of scientific norm, that most scientists may disagree with. How to know if you're possibly incorrect about anything, or I'm mistaken or naive. Exactly. Well, exactly. We don't know. We don't know any of that. All I do know, the only thing I would push back on that is that when you've been around lots of critical thinkers, and you've been in forums with them, and you've been in conferences for over 20 years with these people and debated them, there starts to become, how do you say, a consensus out there. Not right or wrong, but things that people have come to the same conclusion. So, I don't believe it. You tell me. I don't believe it. I tell my father. He doesn't believe it. He comes to that same. What I'm saying is you meet people, we hear things, we end up coming back, and agreements start happening.
I have a comment about that.
No, it's harsh. Go to the crackpot. You want to see harsh about me?
No, wait a minute.
No problem.
About the do we think it's correct or not? I've got a couple of videos out about things about what's real, and one of the things that I say about the particle model is that there is no direct evidence of what we're saying here. Nothing.
Yeah.
Zippo evidence. There is, in my opinion, indirect evidence of the electron and proton and nucleon, which we claim is evident, indirect evidence. Because we don't see them per se, we see there's just no direct evidence. So I claim we can't prove this model without direct evidence. When somebody gets direct evidence of an object pushing on another object and causing it to move gravitationally, and we can see this visually or electronically, then we'll have direct evidence. We won't have to worry about what's right or wrong. We'll know. But there is no direct evidence, therefore it can't be proved. Unfortunately, I can say the same thing about relativity.
But he's going to ask, I know you can go here, but is direct evidence possible? That's what he's asking. And that's a good question.
Yeah, it's a good question. Could there be an instrument today already that's being used that has direct evidence, but they just don't know they're looking at it?
Well, I think
my point is the particle model will help direct where you look for evidence.
Right,
and maybe it will show. But no, there may never be direct evidence, and so there may never be any absolute proof of any theory. The only one that people will accept is the one that works the best.
Right. So the whole thing about the idea, and Jerry's, I think there's something right that he's saying, and that is direct evidence even possible? Does it even matter? What I think it matters is that if you have if you have a model that works, if you have a model that people can use, because in the end there is this thing that we've talked about. There's a couple of things. There is something we've talked about, and that is the morality of science. It's really interesting to come up with all kinds of systems, right? And all kinds of, I've got this whole thing for the way atoms work and whether we can prove it or not. The question is what good are these things? What good is a model if you can't take the model and do something with it for the betterment of our world, even if it's for the understanding? And the whole thing is that should be an important aspect of science. It's a morality of, oh, well, no, we just do it. We have our particle accelerators. We pretend that we find these and we build this and we build a house of cards. You know, the only reason we know it's right is because we're smart and we've done it. We've gone to these universities. You know, it's all, in the end, the way I look at it is if this particle model really is giving us a first shot. That's the way I would say this model is. It's a first shot of really giving physicality to everything in the universe. Then it's worth it. Now, whether or not we've hacked it right or we have it, then, you know, that's different. So, and again, I'm going to get back to this point. I do have something, because and this happens with us. You have to imagine, Jerry, that I've come across people who have been not more isolated, but more isolated. We've had a lot of people come to our conferences who've worked mostly on their own, right?
Yeah.
And no, they think about things. They've had discussions with people, but they haven't had discussions with people like you, Jerry, like me, like my dad, and like the hundreds of other people we know around the world that are over 300 people around the world that are involved with our organization, that when they get together, that we all sort of talk this language. And one of the things I tell people is this. If you work in isolation, people go, well, I don't need to go to the conference. I'm just coming to the conference to tell you about my stuff. My stuff is right. If anybody wants to do with it, then great. Well, the answer to that question is this, and I've told them this. I said, you know what's going to happen? And this is, we've done it. We're doing this in our model. In our model, we have part 2 has 4 chapters on stuff that isn't ours, that we're stealing. And I tell people, this is what's going to happen. Let's say you have your website or your ideas. Someone like my father and I are going to look at it and go, wow, this is amazing. We're going to incorporate it into our model. And not only that, we'll incorporate your idea and we'll modify it. We'll make it even better. And you may not even know it or even care because you're looking at your stuff in this way. And that's what I said. If you don't get out and circulate, if you don't get out and read things about all the models, it's so funny because so many people in our group don't care about our model. They don't look at it, and I'm thinking to myself, guys, you don't know what's coming. And I look at every ether model, every model that comes out there. Jeff Yee is a good example, the energy wave model. It's very good. I read it up and down. I looked at it. I read his book. I watched all his videos. I questioned him about his own model. Now, I'm that way. So if another person comes out with another model, or if I see it, I will look at it and read it super fast, try to understand it. Now, when you do those things, you have much better chance of getting to truths than you do by yourself. And so whether or not you've questioned, you've worked on this, or even had conversations with your friends, it isn't the same. The number one comment I get for the last 15 years, which I've been one of the directors of our group, the Natural Philosophy Group, which are people just like you, Jerry, me, and my father, we sit around for days, and it's all we talk about. And anybody else who's outside of this thinks it's not. But there's one thing I get back all the time. That people come up to me and says, Dave, I'm so glad you invited me to this. I've been working by myself. I didn't know other people were out there that could understand what I'm saying. And not only that, they make comments and they make suggestions and they tell me things they don't like. And they tell me, and then I get new ideas from other people. That's what I'm saying. So when I see things that you're saying, I'm seeing things that look like from these people we've seen who come into our group constantly, who have been not as much, because you even said to me that you wanted to get people and wanted to converse and talk with people. And the scariest thing to do, there's a double-edged sword, is to go to our conference. Why? Because you're going to go out there, you're going to talk about your stuff, and people, you want to go to the worst place to be shot down. It isn't in front of your friends and family. It's not in front of your, science club at home. It's in front of these guys who spend most all of their energies thinking about this stuff, and they know, and they've thought about it, maybe this part of it more than you have, or maybe a group of them have, and they already have answers that you don't have, and then eventually you say, oh yeah, they're right. So that's the kind of thing I'm saying. When I see some of the comments you make, I see that. Because I had the same things. When I got into the group, boy, I sounded like a newbie. And I was a person who thought about science for decades as well. I was making miniatures of the lunar module out of toothpicks when I was 10 years old. So, anyways, you're a critical thinker. You are actually, in my opinion, amazing in the way you think, because I see you as a person who is not running away from even these types of conversations, and I think that's the most important thing. I'm not going to lie to you. I'm not going to tell you that, oh no, come and your ideas. No. The idea is circulating, being around other people. You are going to. My dad and I's model would not exist if we didn't circulate amongst the people we did, right? At all. And when you go to, I remember my dad going to his first conference. I was scared to death. He was going to make a fool out of himself, and not me, but that I put him in that position. And I remember this story I tell everybody. We're going to wrap this up here because we're getting up almost to 2 hours. I'm going to wrap this up. The story is that here I had help me with the movie. He comes up, and of course it ends up being an amazing thing that came out of all this. Now years later we see that. But he's up in front, and I'm thinking to myself, how did I get my father in front of these people, talking about this experiment that we did that had no hope, not because the experiment was good, but the way we were doing it, there was just, on a scale of 1 to 10, it was alpha. It wasn't even a beta test. And then he's up there talking about it. And then he gets a question from somebody who really says, look, there's this problem with what you're talking about and this problem. And I thought to myself, here it goes. He's going to be raked over the coals. And he turns to the guy, Dad knows the story, told a lot. He turns to the guy and says, you think that's bad? This, and this about what I'm doing? That's really bad. And I thought to myself, that's exactly what kind of attitude you need to have. And so, again, I look at it as I'm no longer a newbie because I've got 100 books behind me of people's other works, and most all of them I've read. And so that certainly helps. So,
yeah, there's one friend I worked with closely who had his idea, wrote a book, and finally I convinced him to go to the conference. He had one agenda: sell his theory. He went for a couple of years, and when he wasn't there, somehow we got in contact, and I said, talk to him. He says, nobody's paying attention to me. Nobody does anything with me, so they're not interested in what I do. See, he wasn't there to learn. Yeah. He was there to sell.
Yeah. In fact, we had 2 Finnish guys in the early 2000s, and I took it upon myself. I don't know. I'm always that way. I don't know why. I just do this anywhere I go, basically, with almost any group. If I see people new to the group, I want them to feel like they're welcome or say hello to them. A lot of times they come isolated. 2 Finnish guys came all the way from Finland to the University of Connecticut. I met them outside in the there was a balcony out there, the math room. Yeah. And so I went out there and I was talking with them and all kinds of stuff, trying to make conversation and asking them what they're doing. And they go, I said, there's a problem with this group. And he goes, what's that? He says, this group is full of salesmen and no buyers. But I thought to myself, and I didn't say it, I said, okay, so here's 2 more salesmen, and they never came back because they were there to sell their ideas. They were not interested in actually looking at the truth. The people who do the best are the ones who stick it out and are there, who are always looking at truth, even about their own. I mean, I can tell you when this book comes out, I'm thinking of all the questions people are going to come lambaste us. I just came up with one the other day with this G2 gravity. It's going to we don't have the orbital models for atoms. If we just do it the same way as planets, in our model, all of the atoms should just be smashing together because the G2 gravity should bring all nucleons together. But that's not what happens. Then I think to myself, well, it's not the problem, the model's problem. It's my problem because the level of atoms isn't going to be exactly the same as the level we're at. If it were, it would be, there'd be little people walking around on, the nucleuses, and the electrons would be moons, and there'd be people and civilization. It's probably not happening. So, I question that all the time. But that kind of attitude is the one that's going to get you everywhere. But anyways, I want to thank you, Jerry. I want to thank Farouk and everybody else. I know there have been a lot of other people coming by here. And my father and I put these videos out. And I didn't expect very many people. We've had, just numbers of people, less than 10 people hanging out with us live. But I do want to, in the end, the way I look at it is this. It's a way for my dad and I to record conversations about this model. Because if for some reason, and we have enough people who know us and know the model, that they believe that this is really something, and it is different from other people's models, to put our name on the Principia Mathematica 2 is pretty bold, but we think that there is some possibility that this is something. Then I'm here to record conversations between my father and I. If this model were to be a model that inspired people and they grab onto it because it's giving physicality to things that weren't there, and even if we got things wrong but they're modifying and they're still using the basis of the model, these conversations and what we think and all those things would be important. So it's more of a conversation about what this model is, and that if it's something, here we are. Because people say, why didn't you record? People really like the model and the world's sort of taking this up, and where was your stuff? So that's...
Even though I said
know.
We can't prove it, it doesn't mean it couldn't be
the
right answer.
Yeah, it doesn't
Just because
mean...
I can't prove it doesn't mean it couldn't end up being the right one.
Yeah, and to wrap it up, if you look on our website, for the book Principia Mathematica 2, we didn't put my dad and I did not come up with the title of the book, Principia Mathematica 2. A friend of mine, my best friend actually, Amnon Myers, who is absolutely a brilliant guy, super brilliant, one of those way out there. He and I have worked 30 years with computers and human language, getting computers to understand human language. He got on the phone with me this year, and he told me when I got off the phone to write a paragraph in the book that the book was going to be named Principia Mathematica 2. You are going to do this. He was like absolutely almost dictator-like in his feeling about what this was, and again his feeling was it doesn't matter if it's right or wrong, but it's the first. So I think it could be, a real extension of the Principia, and it could be our next direction in physics and cosmology, the whole thing in its direction. So, we're going to treat it that way, and if it isn't, then we had fun. So.
Yeah, but some of the things the other people, if this is wrong, hopefully, somebody will find pieces of it that are good to work on and take off with something else.
Yeah, that's a possibility too. And I think it's going to happen. But I honestly, the way I would look at it, and because we're sort of summing this whole thing up, we're coming up on the 2 hours, but I would sum it up as our model requires that every force in the universe have a mass behind it. And we are hacking it in a certain way, which means, in fact, in the book I just wrote today about hacking the universe, is because our model brings everything down to every force is a moving mass. There's no no like fields, magical, anything. There's no magical charge, no anything like that. What it means is that we have an infinite amount of hacks or arrangements of how these particles can move to describe the universe. It's sort of what I would call, if you know what a Turing machine is in software, so that is if you have the rules that can do almost pretty much anything. If you write a big enough computer program, you can do everything in the universe with it. Well, we feel that this is a toolkit that can hack the universe, and that there are literally an infinite amount of hacks for the same problem, for the same phenomena in the physics. So I think in that alone is what I think my friend's saying. It's right or wrong, it is a toolkit that you can hack the entire universe with. And so that's why we're trying to treat this as if it could be that. And if it is, great. If it isn't, I don't know what will happen, but okay. But thanks for everybody's support.
Thank you.
We're going to be coming back probably every, I would say maybe 2 weeks about the book. We'll be here on this channel doing the same thing. For people, especially when the book comes out, and then I think what will happen is we will definitely go to every week, because then we'll have discussions and questions, and I think we'll be generating a lot more interest. So, but thank you very much, and congratulations to everybody, like especially Jerry and Farouk, for having great open minds and at least taking a look at what we're doing. And hopefully you guys will, I'm sure, are already contributing to the advancement of science, but we just got to get it formalized in some way. So thanks everybody too who's been watching these and supporting us on Facebook and YouTube. And look for us. No, we don't, even though my dad has said to somebody, I think even in our family, no, we don't have our website where you can buy our book ahead of time. The way we're going to do that is once we get to a point where we know the relative size of the book, we're going to be able to price it more or less, and it'll be a book like this. It'll be colored, shiny pages with very nice graphics. It won't be hard copy, but it won't be cheap either. I think even with us, it's going to be $20 or $30 maybe for our cost, because as the authors, we're going to do it with Lulu, and we're going to order like 50 of them. It depends. If we find out we've got a lot more, then we'll order 100 of them. But the idea was you'll be able to order them ahead of time and be able to. It's going to be
in color, right?
It'll be in color, absolutely, and we'll be able to sign it for you. And it'll either become a really great place for you to put your cups, and or to rip off pages and write notes on it, or to make paper airplanes, or in fact maybe it'll be worth something in the end. All right, thank you very much. You want to say thanks to everybody? Or
yes, thank you, and for those who asked the questions and gave us opportunity to respond to different issues than just talking about the book, because we covered other issues, and that's good. So I appreciate the questions, and hope to see you again and do it in a few weeks.
Yep. All right. Thank you so much, Jerry. And it sounds like both you and Farouk are, from your questions, you certainly be contributing to the flow. And who knows if this turns out to be something, you're going to be like people who know a lot about this already and who know about, obviously, your critical thinkers and stuff. So thank you once again, everybody. And say good night, Dad.
Good night, Dad.
All right. Ciao for now, everybody. Bye-bye. Got to click on everything. Wave goodbye, Dad.